Welcome back to mathkernel. This is the exercise set that goes with the orthonormal basis classroom. For problems, no new theory. 2 are the must-know proofs. An orthonormal system is linearly independent, and the Fourier formula together with Parseval. The other 2 are the computations, reading coordinates off an orthonormal basis in the plane, and normalizing an orthogonal system into an orthonormal one. Every step is on screen. Pause whenever you want to try one first. Problem 1. A proof. Show that any orthonormal system is linearly independent, using only the axioms and the orthonormal property. Pause and try to structure it. Start the way every linear independence proof starts. Suppose a combination of the vectors equals 0, with coefficients a1 through ak. The whole job is to force every coefficient to be 0. The one move that makes it work. Take the scalar product of both sides with a single basis vector, u. The left side is the product of the 0 vector with u, which is 0. On the right, bilinearity spreads the product across the sum, a sum of ai times the product of ui with u. Now the orthonormal property does the cutting. The product of ui with u is the Kronecker delta, 1 when the indices match, 0 otherwise. So every term in the sum vanishes except the one where I equals, and that term is just a. Putting the two sides together, 0 equals a, and was arbitrary, so this holds for every index. Every coefficient is 0, which is exactly linear independence. Note where the orthonormal property earned its keep. For a general orthogonal system, you'd instead get a times the length squared of u, and you'd divide by that positive number. With unit vectors, the length squared is 1, and the step disappears. Problem 2, the flagship proof. Given an orthonormal basis, show that a vector's coordinates are just its scalar products with the basis vectors, the Fourier formula, and that its length squared is the sum of those squared coordinates, which is Parseval. Pause and try both. Because the basis spans, every x is some unique combination of the b's with coefficients c1 through cn. The claim is that each ck is secretly a scalar product. So use the same trick as problem 1. Dot both sides with bk. Bilinearity spreads it over the sum. The orthonormal property replaces each inner product with a Kronecker delta, and only the j equals k term survives, leaving ck on the nose. That's the Fourier formula. The coefficient ck equals the scalar product of x with bk, so x is the sum over j of its product with bj times bj. No linear system. Every coordinate is a single dot product. Now Parseval, which is the same idea applied to length. Take the length squared of x, which is x with itself, and substitute the Fourier expansion into both slots. You get a double sum over I and j. Each term carries the product of bi with bj, and that's the Kronecker delta again, 1 on the diagonal, 0 off it. So every cross term, where I and j differ, dies. Only the diagonal survives, and it's the sum of the squared coordinates. That's Parseval. The length squared is just the sum of the squares of the Fourier coefficients. Pythagoras, read straight off the coordinates. Problem 3, a computation. In the plane with the standard product, here are two candidate basis vectors, and the vector x equals 3, 1. Confirm it's an orthonormal basis, find the Fourier coordinates, rebuild x, and check Parseval. Pause and try. The two candidates are the diagonal and the anti-diagonal, each scaled by 1 over root 2. First job, always, confirm it's genuinely an orthonormal basis before using the shortcut. Each length squared is 1/2 times 1 plus 1, which is 1, unit vectors. Their scalar product is 1/2 times 1 minus 1, which is 0, orthogonal. Two orthonormal vectors in a two-dimensional space are automatically a basis, so this is an orthonormal basis. Now the coordinates, which is where the effort vanishes. The first coordinate is x dotted with u1, 1 over root 2 times 3 plus 1, which is 4 over root 2, equal to 2 root 2. The second is x dotted with u2, 1 over root 2 times 3 minus 1, which is 2 over root 2, equal to root 2. Those two numbers are the coordinates. No system solved. Rebuild to check. 2 root 2 of u1 is the vector 2. 2. Root 2 of u2 is 1 minus 1. Add them and you get 3, 1, exactly x. On the picture, those are the perpendicular shadows onto the two axes. And Parseval closes it. 2 root 2 squared plus root 2 squared is 8 plus 2, 10, and that equals 3 squared plus 1 squared, the ordinary length squared. Coordinates, reconstruction, and length all agree. Problem 4, the last one, a computation. Two vectors in the plane. Show they form an orthogonal system, normalize them into an orthonormal basis, and argue that the span is unchanged. Pause and try. Two vectors, v1 equals 2, 1, and v2 equals minus 1, 2. The plan is, check orthogonality first, then rescale to unit length, never the other way round. Both are non-zero, so the only question is the angle. Their scalar product is 2 times minus 1 plus 1 times 2, minus 2 plus 2, 0. Orthogonal, so this is a genuine orthogonal system, lengths still free. Measure the lengths. v1 has length root 4 plus 1, root 5. v2 has length root 1 plus 4, also root 5. Equal here, but that's a coincidence of these numbers, not a rule. Normalize by dividing each vector by its own length, and note the denominator is the norm itself, root 5, not the norm squared. That gives u1 equals 1 over root 5 times 2, 1, and u2 equals 1 over root 5 times minus 1, 2. Confirm what we built. Each new vector has length 1, and their scalar product is 1/5 times the old product, which was 0, so it's still 0. Orthonormal system, done. Finally, the span. Each u is a non-zero multiple of the matching v, and each v a multiple of its u, so scaling never changes what they span. The span of the u's equals the span of the v's, which is all of the plane. On the picture, the solid arrows sit exactly along the dashed originals, same directions, length 1. That's the full worked set for orthonormal basis. Notice the single reflex that carried both proofs. Take the scalar product with one basis vector and let the Kronecker delta collapse the sum. That one move gives linear independence, the Fourier formula, and Parseval. On the computational side, coordinates in an orthonormal basis are just dot products, and turning an orthogonal system orthonormal is only a rescale that leaves the span alone. Next up, how do you build an orthonormal basis when you aren't handed one? That's Gram-Schmidt, work problems. If this helped, give it a like and tell me in the comments which problem you'd like slowed down. You can support the channel on Patreon, link below. Thanks for watching. I'll see you in the next set.